all hear me?
Yes, ma'am.
Okay, so welcome to the week 2 problem solving session of fundamentals of food process engineering. So, in case of any doubts during the entire session, you can either unmute yourself or you can put it in the chat box and we'll address the question. And in case you have any doubt, you can mail me in this email. You can also ask any doubts if you have of the previous problem solving session. We'll take it up at the end of the class. So this entire week, if you had gone through, have you guys gone through the lectures first of week 2? So accordingly, if you guys have gone through, we'll proceed at a certain pace. If you have not, then we'll proceed at a much slower pace. Have you guys gone through it?
Yes, ma'am.
Okay, so in case you guys have any doubts, just stop me there. So we'll be continuing with all theoretical questions because your assignment 2 is also entirely theoretical. So question 1. The rotational viscometer is suitable for the characterization of dash and time dependent behavior. So it could be elastic, non-Newtonian, Bingham, or none of these. So what is a rotational viscometer here?
Non-Newtonian.
Okay, the answer could be non-Newtonian. What is a rotational viscometer? Anybody knows that?
Methods of viscometer.
Yeah, that is one type of viscometer. So what is the feature of that rotational viscometer? Anybody? Do you guys know what are the parts that make up the rotational viscometer? Or what is happening in a rotational viscometer? So rotational viscometer, generally what happens is there are two parts in the rotational viscometer, one that actually rotates and one that remains stationary. So since one rotates and the other remains stationary, there is some sort of shear stress that is applied to the fluid that is between these two parts. Like say one is moving and one is stationary. The fluid is filled between these two parts, and when you rotate one part, it produces a shear stress on the fluid that is between the two parts. So this is why it is called as rotational viscometer, and it can be used for both Newtonian and non-Newtonian fluids. Example like shear thinning fluids. So rotational viscometer are mainly of two types, or more than two types actually, and most commonly used are one is a coaxial cylinder, the other one is a cone plate system. So in a coaxial cylinder, you have a concentric cylinder that is placed, and you can either have the outer cylinder moving or the inner cylinder moving. So the fluid is filled between these two places, and when you rotate the one of the part with a certain angular velocity, it produces certain shear stress. So that shear stress you can measure, and you know the shear rate. The shear rate is actually proportional to the rotational speed of the system. So the faster you rotate, the more shear rate happens inside the fluid. So you know the shear rate because you know how fast you're spinning the system, and you can measure the shear stress applied to the fluid, and by that way you can understand what is the viscosity of the fluid between the cylinders. Whereas in case of cone plate system, you have a stationary plate and you have a rotating cone, and the angle between the cone and the plate is extremely small. So you will have a very fine layer of the fluid present, and when you rotate it again, a shear stress is produced. But the problem with the cone plate system is when you are dealing with huge fluids that have large particles in it, so that might not be suitable for a cone plate system, since the distance between the cone and the plate is extremely small. If you have large clumps or particles, it might not be suitable for a cone plate system. So as somebody said, the rotational viscometer is suitable for non-Newtonian fluids. So the answer is option B. So question 2. In parallel plate viscometer, there are two parallel plates where one is rotating and the lower plate is fixed, or the upper plate is circular and rotating where the strain is offered to the liquid which is kept between the plates. So are these statements true or false? Anybody has any clue what is a parallel plate viscometer? Am I going too fast? Do you guys want me to slow down or repeat the previous question? You can put it in the chat box if you don't want to unmute yourself. So what's a parallel plate viscometer here?
It has two circular parallel plates.
Sorry, I can't hear you.
It has two circular parallel plates.
Yeah, so as the name suggests, it has two sets of parallel plates which are generally circular in nature. So you have a bottom plate that is stationary and a top plate that is rotating. So this is also another type of a rotating viscometer that we discussed in the previous slide. Apart from the coaxial cylinders and the cone plate, this is also a parallel plate viscometer is also a rotational viscometer where the bottom plate is stationary, top plate is rotated, and the distance between these plates are extremely small, like say somewhere around 1 millimeter is a distance between these two plates, and the fluid is filled between these plates, and the top plate is rotated at a certain angular velocity. So as you can see, there are two plates where one is rotating and the lower plate is fixed. So the statement 1 holds true. So what about statement 2? Do you think is it true or false?
True.
Okay, so the upper plate is circular and rotating, which is true. What about the second half of the question, where the strain is offered to the liquid which is kept between the plates? So you need to be a bit more careful when we are mentioning all these terms such as strain and stress. So when you're rotating a plate, you're actually applying shear stress, not strain. The strain is actually a consequence of the shear stress that is happening. So you're not applying strain, you're applying shear stress, and that shear stress causes a shear rate, and that is how you measure viscosity in this particular viscometer. So statement 1 is true, whereas statement 2 is false because you're applying shear stress and you're not applying strain. It doesn't make sense to apply strain here. So you're actually applying shear stress, and hence statement 2 is false. So the correct answer to this question is option C. Any doubts so far?
Oh, ma'am.
No, ma'am.
So question 3. Which of the following statement is incorrect? A falling ball viscometer is suitable for low viscosity fluids. Force exerted on the ball is only the gravitational force. Net force is gravitational force minus buoyancy force plus drag force. And the wall effect is undesired in viscosity measurement. So which of these do you think are incorrect statements?
Third one is incorrect, ma'am.
Okay, third one is correct. What about the rest? So have you guys ever seen a falling ball viscometer?
2 and 3 are wrong statements, ma'am.
2 and 3
It's
are?
actually buoyancy force minus drag force, I guess.
Yeah. So if if you guys have any prior experience with falling wall viscometer, some of you would have done it in your 11th grade. So you have a very tall cylindrical glass containing the liquid for which you want to measure the viscosity, and you have multiple spheres of different radius or diameters. And what you do is you basically put the ball on inside the cylinder and wait for it to come down. So what you exactly do is you have a certain mark, say from here is start mark and here is your end mark. So you put the ball here, and from the start mark to the end mark you measure the time taken for the ball to come down. So now you know the length of the tube, that from the start mark to the end mark, and you've calculated the time using a stopwatch. So from the length and time you can get the velocity in which the ball is coming down inside the liquid. So when you see the ball coming down inside the liquid, there are three forces actually acting. So one is the gravitational force that depends upon the mass of the sphere. The other one is the buoyancy force that generally happens when you have a solid inside a liquid, and a drag force that actually opposes the gravitational force when the ball comes down. So gravity is in one direction, the rest two forces are in the other direction. So as you said, it is gravitational force minus buoyancy force minus drag force. So statement 2 and 3 are incorrect. Statement 1 is correct because falling ball viscometer is actually used for low viscosity fluids, because you want the ball to actually come down. If it is extremely highly viscous fluid, then it becomes much more difficult for the ball to travel. And what do you think is wall effect here? Have you guys heard of wall effect?
Don't know, can.
So what happens when you have a very large ball and you put it inside a long cylinder? So what happens is, do you guys remember how a velocity profile looks like uh, at the wall?
Very low, man.
Yeah, so the velocity is extremely low at the wall. Sorry, just a minute. So the velocity is extremely low at the wall. So if you have a ball that is very huge and you're putting it through the cylinder, what will happen is the velocity near the ball will be very close to zero. So the ball will actually have an effect on the velocity of the ball. So the ball will actually try to slow down the ball. But during a viscosity measurement, you need to understand the drag force due to the liquid alone, and not because the wall has an effect on the velocity. Are you guys able to understand this? So as the ball becomes very, very large, the regions near the wall, the velocity tends to slow down. Uh, because of this slowing down, the velocity that you observe is not the actual velocity that the ball is supposed to flow in. Are you guys understanding this part?
Yes, ma'am.
Yeah, so the wall will actually try to slow down your ball. But what you need is to understand how the liquid is affecting the ball flowing, I think the ball dropping. So, in case of viscosity measurement, it is always preferred that the wall effect is neglected. So, in order to prevent the wall from having an effect on the ball falling, you need to make sure that the ball size is extremely small. That is, the diameter of the ball is less than 10 times of the diameter of the tube. Only then will the ball be extremely small and it will fall in the center of the tube. So the effect of the ball will not be experienced by the ball. So the velocity that you will observe will only be because of the liquid stopping it rather than the wall stopping it. I hope this is understandable. So the correct answer to this question is option A, which is the force. There are three forces, and it is gravitational force minus buoyancy minus drag force. So question 4. Deborah's number is represented as characteristic time period of material by frequency, characteristic time period of material by time period of observation, time period of observation by characteristic time period of material, and frequency divided by characteristic time period of material. So there's a lot of terms here. So what do you think is characteristic time period of material here? What does it mean? Have you heard? What do you guys understand from viscoelastic fluid? What do you think viscoelastic fluid means? Have you guys heard of viscoelastic fluid? What do you think from the name? What can you perceive?
Semi-solid.
Yeah, both. And what is viscous elastic? I mean, it has both the characteristics of viscous as well as elastic fluids. So what happens if you apply shear stress to a viscous fluid? Like say when you have a water or honey, the moment you apply shear stress, what happens? Sorry?
Flows.
Yeah, so viscous materials, the moment you apply the shear stress, it starts flowing. In case of elastic materials, what do you think happens? Like say you apply a force and then you just withdraw the force. What do you think happens? Like say even a rubber band may say.
Right after it stops.
Sorry?
It goes back to normal.
Yeah. So in case of viscous fluids, it just tends to flow. In case of elastic fluid, it just tries to come back to its original conformation or shape. Whereas in case of viscoelastic fluids, it has kind of both. It tries to come back to its original conformation, but there's always some sort of a deformation because of the viscous nature of the fluid. So let's say at time t equal to 0, I'm applying a certain stress. And after some time, I'm just withdrawing a stress. Ideally, in case of a viscous fluid, you will immediately see that the fluid will start flowing. Whereas in case of an elastic fluid, you will have a similar profile for a strain. That is, your strain will immediately increase and will be there as long as you give the strain, as long as you give the stress. The moment you remove the stress, the strain will also drop. So for elastic fluid or elastic material, your strain graph will also look exactly the same way. Whereas in case of viscoelastic fluid, it is a mixture of both. So when you apply stress, it actually takes some time for the material to adjust to that stress. So the strain gradually increases to a certain point. And the moment you remove the stress, it does not completely go back to its original position, but it slowly starts decreasing. The strain slowly starts decreasing. And sometimes this happens in an exponential manner. And in case of some viscoelastic fluids, it can never gain back its original shape. So there's always some sort of deformation, which is why you don't see the strain completely going back to 0 here. So this is how a viscoelastic profile looks when you just apply shear stress and then remove it. So the time required for a material, a viscoelastic material, to adjust to the stress is called as the characteristic time period of the material. That is, like say if you withdraw the stress, the amount of time it takes to come back to adjust or to come back to its almost original state is called as the relaxation state relaxation time, or the characteristic time period of the material. That is the time it requires to adjust. And time period of observation is your entire time of your process. That is the entire time that it has taken for the applying of the stress and the removal of the stress, which is like basically your entire time of the experiment. So Deborah's number is actually a dimensionless number which is given by relaxation time or the characteristic time period of a material divided by time period of observation. Now let's say Deborah's number is less than 1. So what do you think it means here? From the formula, what can you get if Deborah's number is less than 1? So when is the Deborah's number less than 1?
Liquid. It's more of a liquid when it's less than the
So
number.
yeah, right. So when you have a viscous nature, your Deborah's number is less than is as less as possible. So lesser the Deborah's number, more viscous is the nature. Which means why do you think this is the case? More viscous is the nature. So when you have a viscous material and the moment you remove stress, it is able to it's able to adjust to the stress much quicker if it is a more viscous fluid. So for a viscous fluid, the relaxation time is generally lesser. So the more viscous, the more or less is the relaxation time. So lesser the Deborah's number. So which is why lesser the Deborah number, more viscous is nature in the viscoelastic fluid. I mean, there can be fluids that are more elastic than viscous, and there can be some fluids that are more viscous than elastic. So lesser the Deborah's number, you can say more is the viscous nature contributing to that material. So the answer to this question is option B, which is relaxation time divided by time period of observation. So question 5. Example of Weissenberg effect can be seen in A. jellies, B. oil, C. fruit juice, and D. bread dough. So what do you think is a Weissenberg effect? Okay, so let's say you have a beaker full of water and you just put a rod and start stirring it. What do you observe inside the beaker? So what happens to water when you start stirring it?
The water will go towards the start.
So
It rises now.
water rises or water sinks?
It rises.
Why?
Uh,
Have you ever put a spoon inside a tumbler and seen that water is coming onto the spoon into your hand?
no.
Yeah, so water doesn't rise, water actually sinks. If you put a spoon inside, you will see a kind of a vortex kind of a formation, and your water will actually go towards the base of your vessel. Whereas if you're looking at a cake batter or a bread dough or something like that, those are viscoelastic fluids. So when you put a cake batter and you try to start mixing it, like say you have some mechanical stirrers that are available, if you start mixing it or you put a rod and you start mixing it, you will actually see that the dough is kind of sticking onto the rod and coming up. So in case of Newtonian fluids like water, you will see that when you stir it, the water actually goes below. Whereas in case of a non-Newtonian fluid, say viscoelastic fluid or like a bread dough in this case, when you stir it, it will start coming up onto the rod. So this actually is known as the rod climbing effect or the Weissenberg effect. So why do you think this happens? So in a viscoelastic fluid, when a rod is rotated, it kind of opposes the centrifugal forces and the gravitational force. So it experiences viscoelastic fluids because of its elastic nature. It is when you stir it, it tries to get back to its original shape as much as possible. And in this condition, there is some due to multiple forces that are acting on the viscoelastic fluid, the resultant normal force is created, that is in upward direction. That is when you cancel all the forces in a viscoelastic fluid that is trying to rotate, but it is also trying to get back to its original position. So when you have these kinds of forces, there is a resultant upward force or a normal force experienced. And because of this normal force, you can actually see the liquid or the fluid starting to rise onto the rod. So it kind of opposes the centrifugal force and the gravitational force. So it seems to have kind of a centripetal force here. So this rod climbing is known as a Weissenberg effect and happens because you are dealing with an elastic fluid here. So the answer to this question is option D. Yeah? Any doubts?
No, ma'am.
Okay. So moving on to question 6. In viscoelastic material, the stress required to maintain a certain strain is independent of time, decreases gradually over time, increases gradually over time, or first increases and then remains constant. So what do you think is the answer? In case of viscoelastic fluid, let's say you're applying a certain strain. I mean, you're making sure that the viscoelastic material undergoes a certain strain at say time t equal to 0. But in order for that material to maintain that amount of strain, you should be constantly giving some sort of stress. But the amount of stress that you will be giving will gradually decrease over time, and in fact this decrease is in an exponential manner. So the answer to this question is not option D, it is actually option B. It gradually decreases over time and is found to be exponential in manner. So this is like a property or characteristic part of a viscoelastic material, where it becomes much more easier to give that certain kind of strain in a viscoelastic fluid as the time passes. So this property is actually exploited in something called as a stress relaxation test. Do you guys know what is a stress relaxation test? So a stress relaxation test of a fluid is exactly pretty much the same concept here. So what you do is you have a liquid in hand and you're trying to make sure that it undergoes a certain amount of strain. But to undergo the certain amount of known strain, that is epsilon here, you are applying a certain shear stress to the liquid. But as you see, over time, your stress decreases. So in a stress relaxation test, over time you collect the amount of, you measure the amount of stress that is required to maintain a certain kind of strain. So you get a data of stress versus strain over a certain period of time. So this kind of a data is actually used to fit to multiple models and to understand the rheological behavior of the fluid that you're dealing with. So this is known as a stress relaxation test, where you give a certain constant strain and you measure the stress over time. So when you withdraw, so as you can see, there's a certain amount of time that it takes for the stress to slowly start gradually decreasing, but still maintain a certain amount of strain. So the time it takes to fully relax the fluid or to adjust to the strain is known as a relaxation time. This is well explained in lecture 9 if you guys have more doubts. The answer to this question is option B. It decreases over time. So question 7. A relaxation time is observed when stress reaches certain amount of initial stress, the initial stress that you give. Like say you can refer to the previous diagram. So initially there was a sudden rise in the stress and slowly started gradually exponentially decreasing. So what do you think is the relaxation time in that case? Any other answers apart from 50%? So I can give you a hint. So when the stress decreases, it decreases in an exponential manner. So what is an equation for an exponential decay? How do you, what is the equation that you use to define an exponential decay in terms of y and x maybe? So when you give an instantaneous strain, like say epsilon naught, your stress, as I mentioned in the previous slide, it slowly starts decreasing in an exponential manner. And this is how you actually define an exponential decay. Sigma equal to sigma naught exponent of t naught minus t by tau. In this case, let's assume t naught is equal to 0 seconds. So it will be exponent of minus t by tau. So here sigma naught is the amplitude, that is the initial stress, the immediate stress that it underwent, and t is the time at any point of your experiment, and tau is actually known as the relaxation time. So when your t is equal to tau, what is your equation turning into? Let's say t naught is 0 and t is equal to tau. So how much is sigma equal to? Anybody? When t is equal to tau, what is the equation become? So when t is equal to tau, when you substitute in the equation and you assume t naught to be 0, your sigma equals to sigma naught e power minus 1 here, which is equal to sigma naught by e. So 1 by e is actually 0.368 in value. So sigma equal to 0.368 into sigma naught. So the moment your stress comes down to a value such that it is now 0.368 of the sigma naught, that time is known as the relaxation time. So you can calculate the relaxation time of a fluid by measuring the shear stress over time for a certain shear strain, and from that you can calculate the tau, and the relaxation time can give you an idea of the Deborah's number, the kind of fluid that you're dealing with, whether it is more viscous or less viscous in the viscoelastic fluid. So the correct answer to this question is option A. Any doubts so far?
Oh, ma'am.
Okay, so moving on to question 8. In case I'm going fast, just let me know, we can slow down and repeat the question. So statement 1, this is actually an example of your previous week, so you guys should be able to answer this. Statement 1, thixotropic fluids show decrease in viscosity but increase in shear stress with time. And statement 2, bentonite clay is an example of thixotropic fluid. So which one of these are true and which one of these are false? So let's go to statement 1. What is a thixotropic fluid here? Any other answers apart from option A? Okay, so what is a thixotropic fluid? Is it time dependent or time independent? So in a time dependent fluid, is the viscosity decreasing or increasing? This should be in the week 1 classes as well.
So for thixotropic fluid, uh,
Sorry, we can't hear you clearly. Could you?
for thixotropic fluids, viscosity decreases over time.
Okay, viscosity decreases over time. So what about the shear stress?
So decreases.
So we're talking about we're measuring the viscosity at a constant shear strain or a constant shear rate, and you're saying that because viscosity decreases, so should the shear stress decrease or increase? If your viscosity is decreasing and your shear stress is shear rate is constant, should your shear stress decrease or increase? Yeah, so thixotropic fluids actually show a decrease in viscosity and a decrease in shear stress as well, because your shear rate is constant and your viscosity decreases, so tau equal to mu gamma dot. So if mu is decreasing and gamma dot is constant, tau should also decrease with time. So statement 1 is false. You can actually see the shear stress decreasing with time here in case of thixotropic, whereas in rheopectic it's the exact opposite. So your viscosity increases with time and your shear rate remains constant. So your shear stress increases with time. So statement 2, bentonite clay is an example of thixotropic fluid. Is it true or false? Bentonite clay is actually a rheopectic fluid. So if you just give a constant shear rate to a bentonite clay mixture, it will just start to harden or it becomes much more resistant to flow. So bentonite clay over time actually becomes highly viscous and it is a rheopectic fluid. So both the statements are false here. So the correct answer to this question is option D. Moving on to question 9. In which model is a spring and dashpot connected in series? So we have multiple models here that describe the rheology of a certain viscoelastic fluid. So when you in a viscometer you will get data such as shear rate, shear stress and everything. So with those data and with time dependent data, you need to actually fit the data into a certain model to understand how the fluid is behaving. So we have multiple models here. So which one of these model has a spring and a dashpot connected in series? These are explained in lecture 9 of week 2. You guys know what each of the models stands for, or should I explain that?
Yes, please.
Yeah. So there are four, these are just 4 models. There are actually multiple more models there. So in a kind of model nowadays in viscoelastic, since there is a viscous part and an elastic part, the viscous part tends to flow, whereas the elastic part tends to gain its original position back. So an elastic part can be represented by a spring here. So when you try to apply a force to the spring, it tries to bounce back. So the elastic nature of the fluid can be represented by a spring, whereas the viscous nature of the fluid can be represented by a dashpot. So what do you think is a dashpot? Have you guys heard of a dashpot? You would have seen in one of your day-to-day experiences where you would have encountered a dashpot but maybe not realized it. Have you seen those doors where you just pull open and you just leave the door open? It just slowly starts to close instead of banging. Have you guys come across such doors?
No.
Yeah, so it's actually all those kind of have a dashpot in it. So dashpot is actually a unit that dampens the amount of force that you give. So you just forcefully open the door and you leave it open. It slowly starts to close instead of banging. So there is some kind of resistance that is happening to the door to prevent it from banging back to the wall. So this kind of resistance force is actually given by the dashpot. So when you apply a certain force to a dashpot, it tries to resist the force that you give. So a dashpot is indicative of the viscous nature of the fluid, whereas the spring is indicative of the elastic nature of the fluid. So in case of elastic spring models, they obey the Hooke's law, where your force is directly proportional to the elongation that you give. I mean, the more force you give, the more the spring is elongated. The same is observed in an elastic fluid as well. Whereas in case of a dashpot, that follows the Newton's law of viscosity. That is your force, that is your shear stress, is actually proportional to the rate of change in the strain. This one is directly proportional to the strain, whereas the dashpot is proportional to the rate of strain. So together, when you have both these systems in a single model, it can replicate a viscoelastic fluid. And there are multiple models actually developed to replicate the kind of biological materials that we have. One of them is a Maxwell model, where you have the spring and a dashpot connected in series. There are Kelvin models where you have connected in parallel, and then you have a Kelvin Voigt model where one set is connected in parallel, the other one is connected to the series, that is outside the external of the circuit. And there is Berger's model where both a dashpot and a spring is connected externally outside a parallel circuit. So all these are different kinds of models that were developed over time to replicate the kind of biological materials that we deal with. So after getting your shear stress and your shear rate data, you will fit these into these kind of models, and you'll find out what is E, what is eta here, to give you an idea of how much viscous the fluid is or how much elastic the fluid is. That is, what is the relative contribution or which is more dominant in a liquid. So these kind of models help you to understand the rheology of the viscoelastic fluid that you're dealing with. So in this case, the Maxwell model is the model that has the spring and the dashpot connected in series. So details of this are very thoroughly given in lecture 9 and lecture 10. So you guys can go through that in case of any other doubts. So option C is the answer to this question. Any doubt so far?
No.
Okay. So moving on to the last question. So results of a creep test are given as compliance, shear rate, uniaxial compression, and viscosity. So do you guys know what a creep test is? So where do we use a creep test? Do you guys know that? If not the entire principle of it. So a creep test is also one other test that is done to understand the rheological properties of viscoelastic fluid. So we went across the stress relaxation test, that is, you apply a certain constant strain and you measure the stress over time, which decreases in an exponential manner. That is stress relaxation test. So we have another test known as the creep test, which is the exact opposite of a stress relaxation test. So in the previous one, that is a stress relaxation test, you have a constant strain, whereas in case of creep test, you have a constant stress. That is, you apply a constant force to the liquid to maintain a certain kind of stress, and this period where you maintain this kind of a stress is known as the creep period. So your viscoelastic fluid will not behave like a purely elastic or purely viscous. Like say if it was purely viscous, the moment you apply stress, it will start flowing. So your strain will be like pretty much flat here. Whereas in case of an elastic like a rubber band or something that comes back to its original position, the moment you apply stress, you will have a certain strain, and the strain will remain throughout whenever you apply the stress. And the moment you release the stress, the strain will also go back to its original position, that is 0. It's the exact same as your stress relaxation test, except that what you apply constant is different. There it is the strain that is constant, here it is the stress that is constant. So when you apply a certain stress at say time t equal to 0, there is first an elastic strain. That is, since it has both elastic and as well as viscous nature, the elastic nature of it will give a sudden initial strain here. It's just extremely sudden. So this part is known as the elastic strain, and over the creep period, the viscous nature of the fluids starts to creep in. So you will have a viscoelastic strain, that is your strain will slowly increase with stress. There is no sudden increase or there is no just complete flowing. It will be somewhere in between the both, and you will have a strain that is slowly increasing with time throughout the creep period. And the moment you release the stress, that is you withdraw the stress, there will be an again elastic strain. That is, the moment you release the stress, your elastic part of the fluid will try to come back to its original position. So there is some sort of deformation that is happening here, and once that is gone, again the viscous nature of the fluid will prevent it from completely dropping. That is, the moment you withdraw the stress, everything does not come back to 0. It takes a while to slowly adjust to that non-stress condition, and you will see that your strain is slowly decreasing in an exponential manner. But in a viscoelastic fluid, it never goes back to complete 0, because there is some sort of permanent deformation that happens, and this permanent deformation is known as a viscoplastic strain. So it first shows an elastic strain, that is a sudden increase. Then you have a gradual increase because of the viscous nature. The moment you remove the stress, you will have again a sudden decrease, and then a gradual decrease because of the viscous nature. So this is like a typical profile of a viscoelastic fluid. Whether you keep the stress constant or whether you keep the strain constant, you will have a gradual increase instead of a sudden drop or a sudden flow. So when you do a creep test, you keep the stress constant, and you attain when you can find out the strain that is required. But in all the instruments that you have to measure the creep test, you get the data in terms of compliance. So what is compliance is that it is strain by stress. It is exactly the opposite of your viscosity in this case. So creep compliance is actually strain by stress. But here, since we are dealing with viscoelastic strain, your viscosity is not always constant. That you have to keep in mind. So compliance is actually strain by stress, and you get the data of the creep test in terms of compliance only. So this compliance, you will again fit it to the models that we discussed in the previous questions, and that will give you an idea of how viscous the fluid is and how elastic the fluid is. So these are the kind of tests that we do to understand the viscoelastic behavior of the fluid. Any doubt?
No, ma'am.
Okay. So the correct answer to this question is option A. So all of these are properly and thoroughly mentioned in all of your week lectures, in week 2 lectures. And you guys have any doubts, you can either post it in the discussion forum, you can mail me, or you can view to the lectures as well. None of these are taken outside your lectures. So you'll find the answers to these lectures in your to these questions in the lecture itself. And apart from that, we'll be posting this YouTube video and these PowerPoint presentations in the NPTEL website for you to refer later. So your assignment 2 actually has the same concepts, but instead of a certain given, there will be a certain other question asked. The same concept, but a different kind of a question asked. So hopefully these questions will be